Hi, everybody. My name is Vikram. I'm the guy who just deserted everybody. I started this group back in 2017. I've moved to San Francisco now, and I run the group, similar group over there as well. I was told to not come into the front of this slides. All right, awesome. OK, I'm also co-founder of OmniLabs Inc. OmniLabs Inc. is a company based in San Francisco. We are trying to build a visual language for people to do all kinds of stuff that they do online, and mostly to automate all of that stuff. I'm also Google developer expert for cloud and machine learning. Cloud and machine learning, basically, you can say Google Cloud and TensorFlow. So today, the topic is encompassing both of those. What we are going to try to do is we are going to get you started on machine learning. And hopefully, by the end of the talk, you come out like this. So we'll see. We'll see how much we can do on the training program from starting to the end in 1 hour. And hopefully, if 1 hour isn't enough, we have the full day. We'll do the whole workshop. This is just a presentation. You can, as much as you can take in, good for you. But if not, we will have the full day. We'll go through each and every step of this. And by the end of this, we will be at that point. Too quick. OK, awesome. So for the starters, there is a revolution in machine learning. I hope we all can agree on that. Machine learning is changing everything that is happening in the world right now, be it from very small day-to-day chores to something at a very large planetary scale. This is an image from NASA. NASA and Google Cloud started together to find out more planets in the galaxy, not just galaxy, in the universe. To find out planets, it's a very hard task. Think of stars. We have a hard time trying to just even find out stars, because stars shine bright, and we can find out their digital signature by the heat. It's easy to find stars. But when you have to find out a planet, the signal is very distorted. Plus, there are hundreds of millions of planets that are out there. To find out a planet, you have to do a lot of calculations. And people at NASA have been doing this for a long time, and they have been finding planets all the time. But the issue is the data is very, very distorted. With machine learning, what teams have been able to do is they have been able to use the distorted data again and pass through that same thing, the data that teams discarded. They have been able to find more planets on that. So OK, did not see that. OK, so this is the data, and they found out Kepler-90 system out of that. Not just that, this is a very noisy data, but data sometimes which we don't even consider to be a data of use. An image of a retina. With using image from the retina, Google's AI and machine learning team, which is like Google AI now, they have been able to identify various type of signals about your health just from an image of your retina. Think of that. Like right now, we have to do blood test, CT scan, so many things just to get some understanding of our body. Google's team has been able to identify a lot of those metrics just by looking at your retina. And one of the biggest things that they started this with trying to identify, I think, diabetes, but they were able to find out a lot more signals in that. And now they can find out all types of metrics by just your retina, image of your retina. This is not only limited to big companies. NASA and Google are, of course, leading the efforts in these cases, but there are grassroots efforts on this as well. I don't know which country or state this is in, but a team of scientists and developers came out together to curb the illegal logging of trees and deforestation. They used small devices. They just hung them on the tree. Those devices were streaming audio in real time. They built models which were detecting when is the tree being chopped, so the sound of a chainsaw. And as soon as they detected those, they alerted the authorities. This is something that they did all on their own. There was no big team, maybe a small team, but not a huge team, not something that is an effort by a big corporation. These are grassroots efforts. Also, it's not only limited to developers. This is called NSynth. It's a device which is made by Google team, but mostly by the people who are audiophiles in that team. What they have done with this device, it's NSynth. It's based out of Project Magenta. This device can help you create music without you knowing any music. One of the recent things that they did was piano has so many keys, I don't even know how many keys, but they distilled it down into 6 or 7 keys. And you can play using those keys, and the rest of the piano will follow you to make sure that you are actually generating music. And you can just be smashing keys randomly. So it can help you generate music. So totally in the creative sense as well. Machines are helping you there as well. Very quick. It's not only for fun and doing some random stuff. It's also in production. These devices that you see every day, I know there are a lot of other devices as well. I'm from helping the Google present some stuff. These devices, almost all of them have at least some machine learning component built into them. All of those devices are smarter, and they're getting smarter every other day. You might have seen the Pixel 3 launch. It's such a great camera. All right, all of this is being made possible by using TensorFlow. TensorFlow is the machine learning library which is behind all of this. It is a machine learning platform that is for everyone. And by everyone, I mean everyone. Everyone in the world is using it. The only place I hope penguins are not using it, it's in Greenland. Even there are people in Antarctica who are using it, researchers who are in Antarctica and they're collecting samples. So the Greenland is the only place which we don't know of if people are using it, but everywhere else people are. What is the reason for that? For TensorFlow, one of the core ethos has been to make sure that they are open, they are transparent, and they are open for everybody to participate. And that has been driving the TensorFlow community and overall machine learning research and enablement in general. So what is TensorFlow? TensorFlow, an easy way to understand it, it's tensor are multi-dimension arrays. So tensors are basically how you would represent your data. And flows are just flow of your data through some operations. So the way I start to do that is, let's say your data is an image. You can, of course, represent your tabular data in tabular format. That's like tensor format, that's easy. But what about images? You can represent images as well. There are techniques around, so like right now, we have an image which is just, you can say, is there a color present or not present? And if the color is present, you give it a number from 0 to 1, and that's your final tensor. So you change all of your data, raw data that you have, into form of tensor. And then you create a graph of operations that you want to do upon those. These operations graph can keep changing based upon what you want to do with your data. And this is the majority of time that people spend upon, because the other part is done by data teams, and this part is done by machine learning engineers teams. But both are very equally important on how well your machine learning model does, or how well you do your overall machine learning ecosystem. This graph, the thing that is very special about TensorFlow is their graph that they generate is static, and it can be moved across, and it can be distributed across different types of devices. So this one graph that it is generated at the very end, you can train this graph on a GPU, TPU, small Raspberry Pis, on your laptop, doesn't matter. The thing that was given to us by, initially, I guess, JVM gave us the ability to move things around across platforms. With machine learning, it didn't used to be the case. You could only run it on a very specialized system. It has been changed. There are other libraries which do similar things, but the concept was very initially introduced very well by TensorFlow. Data flow graphs is also a concept that is used in data sciences, if you are familiar with things around there. But TensorFlow utilizes it to do machine learning. So how does it come together? You have data. So let's say we have a picture of a dog and a cat in there. I don't know if there's a cat in there. And what you're trying to do is you convert that data into each pixel has a value, and that becomes your input layer. Then you build your model, which is your activated neurons. A picture goes through this model, or we call this generally network. Your picture goes through this network, and out comes a final inference, which is whether it is a cat or it is a dog. This is, in very layman terms, how a machine learning model works. You pass it an input, you train your model, and it spits out the result. So what we're going to do is we're going to skip demos. We will do demos after the talk while we are doing the actual full workshop. Okay? So this is a TensorBoard demo. We'll do that demo afterwards. How do I get started with machine learning? That's OK. TensorFlow is doing all of these things. People are doing all of those things. But how do I get started with machine learning? First of all, what you have to do is you have to start thinking about your problems in terms of machine learning. But be aware. Don't think of all the problems as a machine learning problem. Some problems could be solved by just a SQL query. So don't overdo yourself. But if you can start thinking about your problems in terms of a machine learning problem, then it's very easy. There's a proper framework around how should you get your data, how should you get started with machine learning and start training your data. So here we have, you can think about it in separate terms. So labels are all your data which is already labeled. Then your predictions are something that you will get at the end of the machine learning model. Model is something that you will build, and there are features that your data will have whenever you are trying to use that model. Okay? So this model right here that we are trying to do is a user, I want to see, would I want to go for a hike or not? Do I want to hike or not? That's the only thing that I want to find out. Most probably not. So this is the machine learning model. We have that, we have defined our problem. We know all the things that we need to put in there. So let's get started. First of all, we need our data. Now data can be in many forms. We have data which is tabular data, images, and even if you convert all of the data back into tensors, this still data might not be enough. You might have, let's say, only 10 features. 10 features might be good enough for a small mathematical calculation, but they are not good enough for a machine learning model. They might be, but most probably not. So what you do is you end up building your more features on top of that. To do that, you can use various approaches. One of those is called bucketing. You can bucket your data into two separate groups, males and females. And sorry, if there are more people in here, non-binary people, I'm just trying to use this as an example. You can do feature crosses. You can use males who are adults versus males who are young. You can use, along with that, like you can create more features by using feature crosses. You can also limit your like ranges. Let's say like payment isn't generally something that can limit, but age ranges. You can try to use hashing of age ranges. So these are different approaches that come in. My favorite one is embeddings. An example that I love to do about embeddings is Google's Translate team. They built a model between language A and language B, and then they built a model between language C and language D, and they used the core part of that model on language X and Y. Without retraining, without doing any training, that model was able to learn those things. Because the model learned to understand the intricacies of language, and it represented those intricacies in embeddings, what we call embeddings. You take embeddings from a pre-trained model, and you embed it along with the other model, and right there you start getting good enough, starting enough prediction and accuracy, and you can get started with that. So, OK, I have my data. I created some more features. What do I do now? So right now comes the TensorFlow. TensorFlow can also help with the other part, but generally people don't use it as much. But let's say right after that, you start using that. What can I do? TensorFlow provides you multiple ways in which you can use it. One is models in a box itself, like a complete model, already trained, done for you. You can start using it. Or you can create your own model with an estimator. Or you can create your own model from scratch. So how does it work in practice? This is called transfer learning. It's an approach that was there for a long time, but I stumbled across it when I saw one of the demos from my good friend Albert. And what we do in here, this is the demo that I presented last year at DevFest, if folks were here. What we did, we had a model that was trained by Google for us, and we retrained the last layer of that model, and we trained it upon noodles, and we identified whether it was ramen or not. And the way it works is you have a pre-trained model by a company which has all the weights, all the architecture, all included in that. All you do is you remove the last layer of the model, you retrain it on your data, and you are standing on the shoulders of giants. Things that they have built and perfected over the years, you just can't get started right there. This is the first thing that I tell people. Don't build your own models if you can use somebody else's. OK, yeah, you can transfer the data. Or with machine learning, you have the ability to build a complex architecture is huge. Like you can keep adding as many things as you want. Researchers have found out best architectures for specific problems. I don't know which one is this. I think this is a language model. But this is, I think, a language translation or detection model. You can use architecture that is already provided to you from these researchers. This is a complete architecture. All you have to do is write this code in Python or in any other language, and you pass your data, and the model gets trained and updated. Or you can create your own models. When we create our own models, deep learning is something that is very much of a hype these days. and it's just justified hype. But what you can do, you can also create a wide model. And one of the best things that works in tabular data is a wide and deep model, a combination of both. So you can try creating your own models. So, OK, but what is a model? What is a model function? What am I trying to do in there? All that you're trying to do in there is you're trying to pass your label data so that your architecture can learn some weights and identify when it is not learning and improve itself. So we call it a network and a feature. Based upon the labels, the network tries to learn some features and tries to minimize the loss. So this, in short, you can talk about this in very simple stuff. You take the training data in, you compute some values out of that. That is your computed loss. You pass your loss back into the machine, and it tries to reduce that loss. What is this loss that we are talking about? So loss function is basically saying, OK, if I wanted to, have you guys played with the question, 20 questions? You try to find out what the other person is thinking, and they tell you that you are doing correct, or you are going away from it by saying warm or cold. That's the thing that is loss function. Loss function is basically a function that you write to make sure that your model knows how good it is doing or how bad it is doing. And if the model knows that it is doing good or bad, then it can correct itself. It says that, OK, last step I did very wrong stuff. Let me correct myself, correct the course, and do something better. The aim is, finally, to come to the least wrong position. Machine learning is very tough and should never come to 100% accuracy. It always comes to the least error, which would be like around 90, 99% accuracy. OK, so now I know exactly what I want to do. How do I do that? How do I actually write my program? One of the best suggested ways that is currently out there is to use Keras, TF Keras, to write your models. So using TF Keras, writing model is very simple. You just define exactly what you want to do. So we said we want a sequential model. We want a dense layer with 64 units. We want to add another dense layer in there with 10 units. And our activation function is softmax. Our loss function is categorical cross entropy. If you don't understand these terms, don't worry. We will have the full day to do all of these things. OK? And I have an optimizer in there. I am trying to make sure that my accuracy matrix is at the highest. We'll talk about all of these things and what you should be focusing upon. That is my model. And finally, I can export that model out. You can train that model. You can do multiple things in there. But you can export that model out as an estimator. Estimator gives you the ability to make sure that your model can run everywhere and a lot of more functions on top. So this is an estimator. Estimator basically gives you a wrapped function around your model. With that, you can pass in input data, and you can train it on that. You can evaluate that model. You can predict directly right there. And you can export the saved model. This is something that was not there for a long time in machine learning. Teams used to build machine learning models, pass it over, throw it over to the engineering team, and the engineering team figured out a month to come to a point where, OK, this model works, and this is now integrated into our system. And next day, you find out, oh, the accuracy sucks. Let's move it back. Machine learning team again spends months, comes back, and then throws it again over the wall. With this, you can export the model right there and identify whether that model works for you or not within minutes. And we will do this all today. All right. You come to the point, OK, my model is out there, but it isn't good enough. I need it to be better. I need to tune the parameters. One of the things that comes with model is you can have a lot of data. You can have a good model, but still there are some things in there which are not 100% automated. Those are called hyperparameters. Hyperparameters in general, one of the examples that people give is number of layers that you want to add into your model, or number of neurons that you should have in your model. All of those are still right now very human-driven, a human intuition approach. For that, what you can do is you can use hypertuning. Hypertuning basically allows you to try a bunch of different parameters, and whichever one works, that is the model that you should be using. That is the parameters that you should be using. So you can keep retraining, and finally, the best weights that work for you are the ones that hyperparameter tuning gives you. To do that, what you should do is you should never do this on your machine, because it will be really slow. You want to try out hundreds of parameters. You should always do this in parallel and over onto cloud. To do this using TensorFlow, only thing you have to do is two places where you have to change it. I suggest people to do this with TPUs. TPUs are very special hardware. We'll talk about that. And with only two changes in your TensorFlow model, you can enable your model to be trained upon these TPUs, or special hardware. How does the TPU chip works? A TPU chip has a lot of processors in there. They try to parallelize your operations, and they do it very efficiently. There's a white paper out there if you want to learn more about it. We will have some demos later in the day where we will show you exactly how TPU does this. But all it does, it enable, like if you can think your CPU does X, then a GPU does 10X, and maybe a TPU does 100X. That's the speed of operations that you're going through. Like the scale totally changes on how quickly your operations can be done. So hyperparameter tuning on Google Cloud, TPUs are only available on Google Cloud right now. So on Google Cloud can be very quick, and it doesn't take much time and doesn't take a lot of memory. We are moving quick. Nice. OK, so finally you say, OK, I'm satisfied with the accuracy of my model. I want to serve it. A model is no good if it is only on your machine. You want to make sure that it is available for others to use onto the internet. For that, TensorFlow has TensorFlow serving. All you do is you package your model, and in the end, you export your model. And after exporting, you pass it. When you export your model, it generates an inference graph. That is the core of TensorFlow, where it generates graphs in the end. And those graphs can be ported to all the different kinds of machines. So you can export that graph and put it onto a server backed by TensorFlow serving, and you have your model available at an API endpoint. OK, but hey, Vic, I love to do offline stuff. I don't want ever to connect to internet. OK, if you want to go offline, you can put your model onto your mobile using TensorFlow Lite. Margaret, tomorrow is her session, I think, after lunch or before lunch. She's going to talk more about how can you use your models into TensorFlow Lite. But TensorFlow Lite basically converts your models, packages them. It even compresses those models so that it can fit on your mobile. It changes the operations. Some operations which are very good for a CPU, a server CPU, or even your machine CPU might not be good enough for your mobile CPU. Your mobile CPU might get overheated, or the RAM isn't enough. So it changes the whole model, compresses it, changes the operations. And the final model, you can export it to your platform, based upon whichever platform you are using it upon. If you want to use it on Android apps, it will give you a Java and C++ APIs. If you want to use it on iOS, C++ APIs, you can even use these models on Raspberry Pis. And it will give you the APIs that you would need right there. All right, so we covered all the devices. You can start the building of a model on any of these devices right there, and you can export it again to any of these devices at the end, giving you a full ecosystem of how to train, how to build, how to deploy all of these models. All right, done. But I don't want to use Python. OK, if you don't want to use Python, you don't know Python enough, there are other languages that you can use. One of my two favorite ones is Swift and JavaScript. Yay. Debbie isn't here. Debbie would always say JavaScript rules the world. OK, so we have TensorFlow JS, which recently came out. And using JavaScript, JavaScript is one of the most popular languages out there. And using JavaScript, you can build your machine learning models. You don't have to rely on Python. I still use Python. I would still suggest that you learn Python, but you don't have to. But OK, our model is in production. All is good. What about tomorrow some new data comes in? How do I make sure that my machine learning models keep getting updated, that my models are always updated not only in the code, but also in the new data that is coming in? For that, you have to build pipelines. And anybody who has tried to do this has always come up to this conclusion: doing machine learning in production is hard and challenging and everything. All right, because why is it hard? Because all the things that we have talked about until now is a very small segment of what a machine learning end-to-end pipeline looks like. The model that you built is one of the smallest components in the whole system. After that, and around that, even before that, comes in a lot of things. Collection of your data, verification of that data, even the data is correct or not. Feature enrichment, we talked about a little bit about that, but a lot of new features, generating new features. Monitoring of your models, analysis, and finally serving and managing all these resources where you are training these or deploying these models. All of these take time. And to build all this system around, TensorFlow is here to help, hopefully. All right. So until now, how was it done until now? This is nothing new. Machine learning has been there since 80s. OK, so until now, what used to happen is every time a team would come up with a model, I told you they throw it across the wall, and the engineering team starts to work on that. Engineering team, what they did is they started to build very specialized systems around those. So if you gave me a linear model, the rest of the machine learning system would look very different than if you gave me a deep neural network. The whole architecture changed on the engineering side. That was how it was earlier. But the promise of TensorFlow is that you can train, that I should be able to train my model in any possible model type with any possible data types, and I should be able to run this model in production in real time and keep doing this pipelining. How does TensorFlow enable this? OK, so let's go step by step. Data collection. So some of the things that we're going to talk now is not just TensorFlow. Because data collection, you can collect the data, but what are you going to do after that? You have to store it somewhere else as well. Plus, collection of data on your machine might not be scalable. So you have to do this on Google Cloud. So we will move into that segment. We have demos. Demos will be later. All right. For data collection, things that people don't talk about generally in data collection is what is the scale? Where is the data coming from? Is the data in real time? Can the data really increase and decrease on the frequency? One good example is today, people are going to tweet about DevFest 18, but there was no activity on that hashtag yesterday. If I wanted to collect the data on hashtag DevFest 18, if I set up only one machine, it might crash today. So what you want to do is you want to build a system which is easily scalable. So you want to build those on Cloud Functions, though Cloud Function doesn't support real time right now, but hopefully soon. You have PubSub. PubSub allows you to do asynchronous communication. You just pass a message into a message queue, and anywhere else in your system, if somebody is listening to that message, they will receive that message 100%. BigQuery. Now that you have extracted your data, you have to store your data somewhere. BigQuery is the best analytics database out there, hands down. You can store all of your tabular data, which we also do relational databases kind of thing. You can put all of that into BigQuery. What you should do is you should make sure that that data doesn't change often. So we call that data analytics data. And analytics data doesn't change. You only keep adding things on top. So for that, BigQuery is really good because it can allow you, one of the examples that is out there is it queries, I think, 3 or 4 petabytes of data. Petabytes, not small. And it is a complex query. And the result is returned within 30 seconds. To process all of that data, to do all of those things earlier, would have been close to impossible within days. You would have to set up machines, you would have to transfer all of your data onto those machines, you have to run a large Python program, Hive, Hadoop, whatever you want to write, and finally the result would come, and then you have to extract that result from those machines onto your final end machine. All of that is done for you via BigQuery. You just keep appending your data in and query using SQL, pure SQL queries. Then we have Google Storage. Not all data can be stored in a tabular format. So you have images, you have audio, you have a lot of other different types of data sets. What you can do is you can store all of the data in Google Cloud Storage. Google Cloud Storage provides you different layers of storing all that data. It could be if you want that data to be archived for later. So you pay less cost on that. You're not accessing that data as much. Maybe there's some data that you want to keep accessing as many times as you want, and you want it on a very low latency. You can put that on a multi-regional bucket so that you can access it from anywhere around the world, and it will be available to you instantly. OK, so we got our data using Cloud Functions and PubSub, stored it into BigQuery and Google Storage. But pure raw data is never enough. You always want to do more feature enrichment on that data. We'll do questions later. We have the full day. So what you want to do is on top, you want to extract some more features. You want to get some more features out of that. People generally do this. All the machine learning people, they generally try to find out new features. But some things that people don't talk about or miss usually is features that you have identified during building of your model might not be exactly the same when the actual final data starts coming in production. So that we call feature reliability. Data that you used to train your model might be very different. All those features might end up being very different when actual real-time data is coming in. What you want is a reliable way to convert and generate those new features in real time. For that, we have TF Transform. TensorFlow Transform gives you one single reliable way that you can get your data, train your model on while you are building your model initially or in real-time pipelines as well. And you get model analysis and validation tools as well. That was recently released 2-3 weeks ago, where you can easily, on your trained model, you can identify what happens if I change the age to something else. in real time. So you can understand if your model has some inherent biases. And this is really great segment into understanding if you are training your model on correct data or not. All right, quick. OK, so for those to do all this data enrichment, the tools that Google Cloud has to offer you are data prep. We will do a demo of data prep. Data prep basically allows all the operations that you can think of on enriching your data very easily from a GUI interface. GUI interface, you don't even have to write formula. You can do all types of queries. Does this column present has any undefined values? Or if it has big address bar, I want to split it off into country in a different column, city in a different column, zip code in a different column. And it will do all of that for you from UI. And finally, it spits out Dataflow job. Dataflow is a programming language model which is based on Apache Beam. Apache Beam is used to do real-time, high-frequency data ingestion tasks. It does real-time as well as batch. So you can do both. So data prep, a GUI-based model where you can do all of those things. And finally, it gives you a task that you can run on cron job or based upon other triggers. You can say every time somebody requests my data, run this whole job again. With that, if you don't want to do these things, or maybe your engineering team doesn't have those capabilities right now, even though all of that is GUI, you should be able to do this. But if you'd want to do something different, you can use Dataproc. Dataproc is Hive Hadoop clusters that Google Cloud provides you. So if you are familiar with Hive and Hadoop, you can use those here as well. Demo, we'll come to that later. All right, let's say I have all of this now. I have trained my data now scalably, and I have done feature enrichment. Now I want to actually train my data and make it available for people to use. Training your model can be a difficult task if you haven't done it before, basically. If you have done it before, you have some estimation around how many machines you would need, how many CPUs, GPUs you might need, and what is the basically configuration of your machine learning cluster. But here comes two more problems that people generally miss. One is continuous retraining. One of the things that we were doing earlier is we used to get data at the end of the day, and we had to retrain that whole data and make sure that the model is updated for tomorrow, because the predictions that we want to make tomorrow should be also include the data that was yesterday there. So to keep your models updated, you need to retrain your data. And models keep increasing every day. Your data keeps increasing every day. So every day, you're going to pay more than what you paid last day. For that, TensorFlow has ability to do a continuous retraining pipelines. And one of the things that it does, it gives you a pre-built model that you can save as a checkpoint. And from there, right there, you can start a model. And it takes less than a few minutes to retrain your data on, depending upon what is the size of your new data set. But it takes very small amount of time. You can just train it on new data set. You don't have to train it upon all the data set that you had until now. That's continuous retraining. Warm starting. This is the problem that people face in APIs. The models that these TensorFlow or any machine learning system spits out, they're huge files. They're 400 MB file. And let's say if nobody was querying your API for the whole night, and 9 a.m. in the morning, everyone comes in, and everyone wants to know the predictions, everyone is going to ping your server, and your server will be like, OK, let me load 400 MB of file. Then only I can reply to you, because that is my model file. So it will take a long time for it to load that file, and that is called cold start. To do that, TensorFlow provides you a way to warm start your model. It will load your data as it needs, and model converges faster, better quality, and not only in production, but it can also do this while training. So you can load your checkpoints easily and quickly. OK, so what does Google Cloud do this for us here? Google Cloud provides you machine learning engine, one single platform to do all of your training, all of your inference. You can pass in, all you have to do is you pass in your model, and it can keep retraining your data whatever frequency you want, whatever triggers you want it upon. It gives you APIs which are versioned. So tomorrow, yesterday, you built a model. You named it version 1. Today, you got some more data, and you built a new API version. It generated a new API version 2 for you. You check both of the versions. If version 1 is still better, you let your traffic be on version 1. You don't have to redo or redeploy your models and come up to the whole pipeline again. All of that is handled for you by machine learning systems. Plus, it gives you best-in-class hardware. All the GPUs, all the TPUs, TPUs, tensor processing units, we'll come to that, are available on Google Cloud, best in class. As soon as they come into market, they're available on Google Cloud. Hopefully, it continues that trend. Demo, we will do that later. OK, but hey, Vic, we talked about this. I don't like cloud. I want to stay at home. I want to go offline. Or maybe some companies, what they want to do is they want to do multi-cloud. I don't want to be stuck onto Google. What I want to do is I want to be able to move around these clouds. What you can do in both of those cases is you can use these open source libraries, which are provided by TensorFlow team and Google Cloud's team. TFX is one whole set of library where you can have all the operations that your machine learning systems use. And all of those systems that we talked about, TensorFlow Transform, data validation, TensorFlow Serving, all of those are open source projects and are available to you under TFX. And there are more that are coming in there. Another one is Kubeflow. When you have all of these systems ready, how do you actually start doing these things? And how are you able to move things around? So if people are not familiar with Kubernetes, hopefully there is a presentation this year. If not, there will be more sessions throughout the year. But Kubernetes has a project called Kubeflow, and Kubeflow allows you to do machine learning at scale in a packaged Docker environment. And you can move that across to any cloud, onto your local systems, onto different clouds or clusters that are in your backyard. All right. Finally, end-to-end workflow. All of these things are available as open source. You take your model on your training data. You can transform your training model data using Apache Beam, Dataflow, and TensorFlow Transform. You can save your model graph. All of that is available on open source. Finally, you can export your model out. And using TensorFlow Serving, you have the model out and serves out, as well as you can do model analysis. All of this is open source, is available to you. I prefer to use Google Cloud. I suggest people to use Google Cloud, scalable and totally reliable, but you don't have to. All right, so we talked about components of a production system. Production system this is the overarching view of what a production system for a machine learning system should look like. Doesn't have to be, but this is what it should look like. All right, what do we have today? Today, we have tuner, data validation, TensorFlow Transform, trainer, analysis, and serving. All of these things, these components are already present right now, available to everybody to use. What are coming soon? Soon, we will have integrated front end for management of these jobs. These are all the things that are happening in Kubeflow project, so you can keep tab on what is happening in there. A shared configuration across teams, so you can even move a model across teams, or the whole organization setup. OK, we talked about multiple times about cloud TPUs. What is cloud TPUs? So cloud TPUs, you can see the performance numbers right here, 180 teraflops when it was version 2. Then last year, or this year, somewhere in July, they announced cloud TPUs version 3. For the first time, they had to use liquid cooling. They couldn't rely on normal heat sinks. Now it's 420 teraflops. That's huge. You can do whatever you want. One of the data sets that they gave out was ResNet. ResNet 50 is a model. I wouldn't suggest you train it on your machine because it would take days. If you were to build your own compute cluster, it would take hours. But with using a full TPU pod, which is 8 TPUs on a single board, you can train that model in 15 minutes. 15 minutes for a model which used to take weeks to train. That's fast. And you can keep iterating on this. The only thing I think of is how quickly can I iterate on compute engine or compute in general. Whatever I'm doing, whichever problem I'm trying to solve, whether it's building a website or building a machine learning model, as quickly as you can iterate, you will improve. So ResNet 50 on cloud TPUs in less than 15 minutes. What about model building? Do I have to actually build the model? Can we not automate that part? For that, we have AutoML. AutoML allows you to just pass in your data. You don't need to know about programming at all. You just pass in your data, computes, and all the models that are available to you by Google. What they try to do is they try to identify your data type. They try to say, OK, what is your problem? Let's try to find out these hundreds of models that we have available, which one of these models could solve your problem. Then let's do hyperparameter tuning on those. This is not a person. This is all automated, all happening in the backend for you. All you have to do is put your data up, And in the end, it will do all this processing, find out the best model with the best trainable weights, and that is the model that it will give you as an API. And you can use it. To learn more about this, tomorrow Dan is going to do a full workshop on this. So if by end of today you are not happy with me, my presentation, my workshop, you can always go to Dan's workshop and do all of this without doing any code. The thing that it gives out, those models are very, very complex, and they are weird. Like, normally when I'm building a model, I don't have to think about taking the weights from my last layer up to my first layer. I would never do that. So these models are not simple models. The machines are coming up with very complex models. But we don't have to worry about that, how complex the model is, if it works. So the accuracy we see generally on all the models that are generated by AutoML is better than what it is by models that are done by humans. Not only on the large, huge models, but also on the small models. Models that are very small, like you see the size on the operations. Even for the smaller models, the accuracy is higher than what you would do as a human. So AutoML is there to save everybody. All right, what I generally suggest people to do is to not get involved with one or other approach. Try to mix them together. Try to start with AutoML. Understand if your problem is even a machine learning problem. Can you solve it using machine learning? If it works, keep using that AutoML part and build on top of that. Build your machine learning model. That gives you a good baseline. Now you can build on top of that because you as a human have better understanding of your data. Machines don't have that understanding. They try to figure it out, but they don't have that intimate understanding of your data. So you should be able to do all of that on your own. Then do trial and error. Make sure your iteration frequency is high. Keep iterating. You will come to a good solution. And do that on GCP because you have good access to compute and data. All right. To stay in touch, make sure that you keep learning. If you like to read things, go to blog.tensorflow.org. If you like to watch videos, youtube.com/tensorflow. And for anything else that is community-wise, you can go to tensorflow.org community. TensorFlow is very open. They are trying to come up with a new version, TensorFlow 2.0. They are trying to deprecate some things. They are coming up with new ideas. All of those ideas are in public. You can go in, you can comment, you can say that I like this one, I don't like this one because I do something else like this. And they take that feedback seriously. They will come back to you and provide some suggestions or not do that stuff. All right, hopefully we are at this point where you can trust me, but don't do that. So for that, we have the full day workshop. This was hopefully good, and rest of the workshop, we'll make sure that you don't do that. Okay? Questions, we will do after in 2 minutes. Okay? Awesome. Thank you, everybody.